So tonight we discuss the design of reinforced concrete, considering the working stress design or working stress design. So this method of design is considered as an alternative in our NSCP code. Okay. So the working stress design is mainly used in some highway structures, a fluid containing structures, and in the determination of deflection calculation. Okay. So sa ngayon, more on strength design or the ultimate strength design na yung ginagamit natin sa concrete structures. But still, you can use the WSD in your projects. Okay. So in working stress design, there are uh, three assumptions. Okay. In number one assumption, plain sections before bending remains plain after bending. So meaning whatever is the cross section of the member, for example, rectangular. So after bending, still considered as rectangular. Otherwise, the derivation or the formula that was derived using the flexural formula is not anymore applicable. Okay. So second, the stress is proportional to the strain. So that is Hooke's law. Okay, meaning the uh, the farther the okay. So number third assumption is the tensile strength of concrete is negligible. Okay, although there is a tensile capacity of concrete, normally around 10% of the compression strength. Okay. Then number four, there is a perfect bond between steel and concrete. So there will be no slippage during the use of the beam. Okay. So in working stress design, the stresses and K is assumed to be 0.45 of F prime B. So as the relative strength, only 45 to 1 the passive strength is used in this. Okay. For the tensile portions, we have two common type or common grade of reinforced steel. We have the grade and grade 60. So this grade 40 is equivalent to 40 KSI or 275 megapascal. So 275 megapascal. And for grade 40, grade 60 or 60 KSI, concrete. So for the elasticity of steel, is this constant to be 200 gigapascal. Then for steel, concrete, is it 4,700 square root of FM? So it's a function of the compressive strength of concrete. Okay. So in working stress design, we have yes.
So nawala po
Yes.
yung presentation po. Baka po sir, nawala ka po saglit kanina.
Nawala yung?
Nawala ka po sir, na-disconnect ka po.
Okay, sige. I-open lang siguro yung video. I-open lang yung video para hindi masyadong ng internet usage.
Sige po sir, salamat po. Sige po sir.
Okay. So for the load combination in working stress design or the alternate design method, we have 5 load combinations. So all load combinations are unsort. Yes.
Sa excuse po, hindi pa rin po nakikita yung PowerPoint po.
Okay. Yan, nakikita nyo na?
So, sir, kita na po. Salamat po.
Nakikita nyo na yung PowerPoint?
Yes po, sir,
Okay.
kita na po.
In working stress design, we have 5 basic load combinations. Okay. So number 1 load combination is dead load plus F, or the fluid pressure. So for building design, normally wala man tayong for regular building, wala tayong fluid pressure except where meron siyang amenities like the swimming pool. So for beam, so the first load combination is just simply the dead load, or the load itself plus the superimposed loads. Then second load combination is dead load, hydrostatic pressure, fluid pressure. So take note that in second load combination, there is a presence of dead load and fluid pressure plus the hydrostatic pressure, live load, and temperature. For design, normally the present is only dead load and live load. So the temperature load, there is a temperature load, but this is very small compared to the other loading. So to simplify, in the beam design or flexural design, just simply dead load plus live load. But of course, if you have hydrostatic pressure, like in the case of you have basement beam, okay, so you need to consider the hydrostatic pressure. Then the third load combination is dead load, hydrostatic pressure, fluid pressure, plus live load or rain load. Okay? So normally the rain load is again very small. So wala naman tayong, unless that there is a funding, saka yung rain naman tayo hindi ganun kalakas compared to other countries. Okay? Very minimal yung effect niya dun sa structure. But if you're considering for the design of, for example, we have roof slab, so you can consider that rain loading. Then the fourth combination is combination of dead load, hydrostatic, fluid pressure, and 75%. Okay, so 75% considering the presence of live load temperature, or roof live load and rain. Okay? Then the fifth combination is the combination considering wind loading or seismic loading. So for reinforced concrete design, for a medium-rise to low-rise building, wind loading will not burn. So the burning case will be the combination of earthquake, okay, and dead load. So take note that in this case, with earthquake, the combination is only dead load and earthquake. So hindi nagsasama yung wind loading plus earthquake. Kasi bibihira naman na may bagyo ka na nagkakaroon ng lindol. So napakaliit ng probability na. And also, we will notice wala tayong live load, okay, during earthquake. So kasi napakaliit ng probability na nag-earthquake ka, meron tao. Kaya di ba kadalasan pag may earthquake ka, meron tayo doon earthquake, what we need to do is lumalabas agad tayo, di ba? So hindi kino-consider yung presence ng live load during earthquake. Okay? Okay. So in beam or reinforced concrete beam, at small loads, when the tensile stress is less than the modulus of rupture, okay, the bending tensile stress, at least the concrete begins to crack, the entire cross-section of the beam resists the bending. So meaning, pag wala pang cracking na nangyayari, yung concrete natin can resist tension. Okay? So, di ba yung beam natin, for a simply supported beam, we have for vertical loading, the top fiber of the beam is in compression, and then the bottom fiber is in tension. So there is a code requirement wherein there is allowable rupture. So meaning, merong allowable rupture strength or rupture stress before the concrete cracks. So in the code, the allowable rupture is 0.7 of F prime C, or the 28-day compressive strength of concrete. So this is the typical beam section with tension reinforcement. So for uncracked section, this tension reinforcement, hindi pa siya kumakarga nung any bending moment. So before nakumarga siya ng stresses, kailangan mag-crack muna yung concrete section sa tension side. Okay? Then the cracking moment, so ito yung moment capacity before the concrete cracks. So the cracking moment is equal to rupture strength Fr times moment of inertia divided by Ys of T. So this is the beam formula for homogeneous beam. Okay, the Y is the distance from the centroid. Okay, from the centroid to the location of the outermost fiber in tension. Okay, so this is the concrete crack, okay, elastic range. So before it cracks, so yung portion ng mga beam na hindi nag-crack, ang nagkikarry doon is yung cracking moment niya. So the cracking moment is small compared to the crack section. So kunyari meron tayo ditong reinforcing bars. So sa portion na to, gumagana na yung reinforcing bars. Pero beyond the cracking moment, itong portion na to, so hindi pa gumagana yung tension reinforcement. So ang nakikarry pa lang ng any flexural load is the concrete o yung beam pa lang, bottom tension reinforcement capacity ng concrete beam. Okay? So kaya nga may mga cases na not necessary na nag-crack yung beam mo, nakita kay crack sa bottom niya, na babagsak na yung beam yun. No? Ang only implication lang nun is, pag nagkaroon ng cracking, ibig sabihin, gumagana na yung tension reinforcement mo. Okay. So ito yung stress diagram considering ultimate strength. So this one we're going to discuss on the ultimate strength design. Okay, so take note that in ultimate strength design, the shape of the stress is parabolic. Pero in working stress design, the stress diagram is just simply straight line formula siya. So makita nyo dito, yung compression part is yung half lang, portion lang nung beam. Ito lang yung compression part niya. Then all the concrete on the lower or the below the centroid or below the neutral axis of the beam is wala siyang tulong sa capacity. Okay? So let's try this sample problem. So mapapansin ninyo, kahit unreinforced o wala pang reinforcement yung beam nyo, meron na siyang flexural or moment capacity pero napakaliit. Okay? So this sample problem illustrates the cracking moment capacity of any rectangular beam. So in this case, the beam section is 300 by 450 millimeter. Okay, so we have 325 millimeter diameter reinforcing bars. But if we are going to determine the cracking moment, wala pang contribution yung steel reinforcement natin sa bottom. So from the formula, the cracking moment Fr is equal to 0.7 square root of F prime C. Okay? Then the cracking moment capacity MCR is equal to Fr times moment of inertia divided by twice of T. Okay? So for rectangular section, the centroid is located at the mid depth or the mid height of the beam. So yung centroid natin is equal to 450 over 2. It's just simply equal to 225 millimeter. Okay? So the moment of inertia, centroidal moment of inertia, okay, INA, so just simply IG is equal to BH cubed over 12. So in this case, B is 300 times H. So the total height of the beam is equal to 450 cubed divided by 12. So we can now have the centroidal moment of inertia. So in determining the centroidal moment of inertia, we always neglect, okay? We always neglect the reinforcing bars before it cracks. Okay. And then YT, or the distance from the centroid to the outermost fiber in tension. So if the centroid is mid height of the beam, so YT is just simply equal to 225 millimeter. So YT is 225 millimeter. Okay? So the cracking moment, okay,
Sir,
will now
excuse
simply
me po.
MCR is
Sir?
equal to 0.7. Yes.
Sir, excuse me po, hindi po
Yes.
ata masyadong visible po, sir, yung nasa board po. Naka-ano po yung kulay niya, sir.
Okay.
Medyo blurred po. Thank you po.
So the cracking moment MCR, okay, is equal to 0.7 square root of F prime C. So F prime C is 28 megapascal times IG. So yung IG natin, ilan to? Ano yung ba ng IG? 300 times 450 cube over 12. 300 times 450 divided by 12. So this will give 2.278 times 10 to the 9. So 2.278 times 10 to the 9 divided by y sub t of 225 millimeter. So the cracking moment is 0.7 square root of 28 times 2.278 to 9 divided by 225 divide 1,000 squared. So the cracking moment capacity is 37.51 kilonewton meter. So meaning, kahit pa pang reinforcement, yung beam natin, meron siyang 37.5 kilonewton meter na flexural capacity. Okay, so later, we will compare this considering the reinforcing steel. So ano ba yung magiging capacity ng section natin pag meron siyang reinforcing steel? Okay? Okay. So these are the steps in designing the single reinforcing angular beam using the transform area method. So in the transform area method, okay, so let's say for example, this is the typical beam section with dimension D and D. So take note that the D is the distance from the centroid of the bars to the outermost fiber in compression, or it's just simply from top of the beam to the centroid of the reinforcing bars. So ito yung H natin. Yung H natin is the total height of the beam. Okay. So in the transform area method, so we transform the steel into equivalent concrete section by multiplying the modular ratio N. Okay, so the equivalent area of steel is simply equal to N times AS. Okay, so this is the stress diagram. So take note that the stress diagram for working stress design is linear. Okay, the FC is equal to 0.45 square root of F prime C. And this Fs, okay, so although the strain is directly proportional to stress, but considering the steel, the stress capacity of the steel is n times the capacity of concrete. So if we consider this one as Fc, so we just divide the allowable stress of steel Fs divided by the modular ratio. So pag kinonvert din natin yung equivalent stress ng steel into concrete. Dito, kinonvert natin yung equivalent steel area into concrete, but in this case, kinonvert naman natin yung equivalent stress ng steel into concrete. Kaya meron siyang divisor na sa modular ratio. So first step in determining for the transform area is to locate the neutral axis. Okay, so locate the neutral axis. Okay. The moment of the compression area. So how to locate the neutral axis? Moment of area above. Okay. So moment of area above. To area na to. Area times centroid, bar Y1, is equal to the moment of area below. So NAS, so ito, times twice of 2. So once you solve for the neutral axis, okay, then compute for the moment of inertia of transform section. So ang i-consider nyo na determining for the moment of inertia is yung compression above plus the equivalent converted to transform area ng steel. And then using the stress formula, stress is equal to MC over I, you can also solve for the moment capacity of the section. Okay? So parang basic lang to ng mechanics ninyo. Okay? Mechanical static bodies na yung flexure formula na derive nyo sa mechanics is simply just similar to the reinforced concrete. Kasi kinonsider natin to na homogeneous na kinonvert lang natin yung steel into concrete section para maging homogeneous siya. Okay. So, let's try this problem. Okay. So, calculate the resisting moment to the beam shown in figure using the transform area method considering 20.7 megapascal concrete and grade 40 reinforcing bars. So, for grade 40 reinforcing bars, ang FS natin or the allowable stress on the steel is 140 megapascal. So the given beam dimension is 300 by 500 H, the height, and the effective depth D is equal to 425 millimeter. So the area of reinforcing steel is 1,940 millimeters squared. So the equivalent transform section NAS is just simply 9 times 1,940. So in this case, the N is given. So natin na N is 9 for this given problem. But in design or in investigation problem, kailangan lang kunin yung equivalent ES over EC ratio. Okay. So let us assume that the neutral axis is in this station. Okay. Then solve for the centroid. So let's say the centroid
Sir, excuse me po.
to the outer. Yes.
Hello, sir. Medyo parehas po kasi yung color ng pen tsaka po yung color ng background po na sinusulatan niyo po, sir. Hindi po namin nakikita yung
Okay.
solution po. Kung maaari
Sige,
po,
sige.
pa-change po yung... Sir, maraming salamat.
Sige, palitan ko lang yung pen. Okay. So in this problem, so let's assume na yung values niya o yung modular ratio is equal to 9. Okay. But in real design, you need to compute N is equal to ES over ES of C, or just simply 200 times 10 to the 3 megapascal divided by 4,700 square root of F prime C. So take note that determining for N, always get only the two number. For example, kuha nyo ngayon is 9.2. So say N is equal to 9, 10.5. So say N is equal to 10. Okay? But in some other books, they consider the decimal, okay, decimal value of N. Kapag kinumpare nyo, maliit lang yung effect sa moment capacity. Okay? Ipigyan ko ito yung slide para sa solusyon. Okay. So how to solve the neutral axis? So the moment of area above is equal to the moment of area below. The moment of area above is equal to 300 times x. So the lever arm, if this is x, the lever arm is just simply x over times x over 2 equal to the moment of area below. So the moment of area below, so the effective depth is 325. So the distance from the center of the bar to the centroid of the section is equal to 425 minus x. So the area is 9 times 1,140. So this is NAS times the lever arm. So the lever arm is 425 minus x. So 425 minus x. So from this, we can solve for the value of x. What's the value of x? Can you please solve? Can you solve for the value of x? Anybody?
Sir,
Yes.
171.707 po.
171 point.
171 po.
171 point
71 po.
71
Yes po.
millimeter. Okay, thank you. So after solving for the neutral axis, the equation of neutral axis, then we can now solve for the resisting moment. So the resisting moment is just simply the stress multiplied by the lever arm. So for this problem, okay, ito yung compression side niya. Then ito yung tension side. So resisting moment, okay, ito yung stress diagram. So triangular, and ito yung tension niya. So we have like this one. So this is FC, which is equivalent to 0.45 square root of FMC. But just simply 0.45 square root of 20.7 megapascal. 2.047 megapascal. Okay. So this value, so this centroid value X is equal to 171.71 millimeter. Then the friction S is equal to 140 megapascal for grade 40. Grade 40 yung bakal natin. Okay, grade 40 reinforcing bars. So grade 40. Okay. So from the internal couple, so the centroid of the compression is located 1/3. Okay, di ba yung centroid ng triangle natin is 1/3 of 171.71, or just simply equal to 1 divided 3, 57.24 millimeter. So merong couple, okay? Ito yung resisting moment na tinatawag natin. Couple, internal couple, considering the compression and tension. So this internal couple will have a lever arm equal to D minus X over 3, or just simply 425 minus X over 3. So 425 minus, so X over 3 is 57.24 millimeter, or equal to 67.76 millimeter. So considering steel, so you can take moment either on this side or on the compression side. Okay? So considering, take a moment about steel section. So moment capacity is equal to, so kukunin mo na natin volume. So para ito yan eh. Meron tayong stress, triangular stress with dimension B. Okay. So ito yung B natin is 300 millimeter. So this dimension is 171.71. Then this dimension is equal to FC. So the moment is equal to 1/2 volume. 1/2 times FC, 2.047 times, okay, triangle, this triangle, 171.71 171.71 times D, para mabuo natin yung millimeter, times the lever arm of 367.76. So the moment capacity is just simply, so 1/2 times 2.047 times 171.71 times 300 times 367.76. Okay. Oh, masyado maliit. Para mali yung value. 0.5 times 2.047 times 171.71 is 300 times 367.76. Okay. The moment capacity is 1,938.96 kilonewton meter. Okay? So, same true with pag ginamit nyo naman yung mag-moment kayo dito, dapat na nalabas yung value is parehas lang. Okay? So, magbigay mo tayo ng 5 minutes. Meron lang akong tawag sandali. Okay. So, okay. So, ito yung moment capacity ng concrete. Okay. So, then, considering, if we take a moment, okay, considering taking moment at, okay, compression side, okay, concrete. So, the moment is just simply stress times the area. So, ano yung equivalent area ng concrete? So, N times AS. So, 140 times 9 times 1940 millimeters squared times the lever arm. So, the lever arm, either take a moment on the steel or take a moment about the centroid of the concrete, just simply D minus X over 3 or 367.76. So 367.76. So the moment capacity is equal to 140 times 9 times 1940 millimeters squared times 367.76 millimeter. So the moment capacity is 898.95 kilonewton. So ito yung moment capacity considering steel. Ito yung moment capacity considering concrete. So what does it mean? So ibig sabihin, if you are going to consider the crushing strength, so yung magpipail na yung steel, concrete natin, ang kaya niyang kargahin na moment is 1,938.96. While considering steel, ang kaya niya lang is 898.95 kilonewton meters. Ibig sabihin, mas unang mapipail yung steel natin compared to concrete. Na yun yung magandang design. So dapat mauna mag-fail yung steel bago yung concrete. Bakit? Kasi pag unang na-fail yung steel, ang tendency is makakakita muna kayo ng cracks sa beam. Okay? So pag nakita kayo ng cracks sa beam, meron kang possibility o malaki pa yung chances na malaki pa yung time para lahat yung occupied ng building is makalabas nung loob ng building. So baka siya mag-fail. Kasi yung, di ba papansin ninyo, kung matatanda ninyo, nagkaroon kayo ng testing of materials, kung nag-test kayo ng steel reinforcing bars, kung nag-fail yung reinforcing bars, ang failure niya is dahan-dahan. Mag-elongate muna, di ba? Habang nag-apply ka ng load, di ba, sa universal testing machine. So, yung steel bars natin, hahatakin siya. Okay? So, bago mag-fail yung steel, pag hinatak mo siya, mag-elongate mo na yung steel. So, matagal yung time ng elongation bago ma-break yung specimen, steel specimen natin. But, in concrete, okay, sa compression machine, apply ka ng compression, wala kang makikitang changes dun sa concrete. Hindi siya umiiksi hanggang marinig mo na puputok na siya, di ba? Kung pumutok ka siya, nagtina siya. So compared to testing ng reinforcing bars to failure, mahaba to. Ilang seconds yan. Okay? Pero yung compression failure, pag nag-crack na siya, kinumpress mo siya ng kinumpress, bigla siya puputok na lang. Less than a second, puputok na yung concrete sample natin. Kaya yun ang advantage kung bakit kailangan mauna mag-fail yung steel compared sa concrete. Sa steel, merong warning, may kahing ka makikita. Pero sa concrete, wala kang makikitang cracking. After cracking, bigla siyang putok na wala na siyang stand. Babagsak magad yung structure natin. Okay? So any question? So ito yun lang, ito parang ano to parang review lang to nung mechanics ninyo, strength of materials. Okay? Di ba yung last part ng strength book ninyo is about bending capacity of the homogeneous section. Meron doon concrete, meron doon steel, meron doon timber. Okay. So yun yung capacity considering the internal couple. Okay. So let's say subukan naman natin yung capacity o sorting for capacity considering yung prescribed na transform area method. So transform area method, the first step is to locate the neutral axis, so similar sa ginawa lang natin. Then second is to compute the moment of inertia and compute the stress using flexure formula. So the only difference is dito, compute lang yung moment of inertia, unlike dito, kinumpute natin, sunod natin yung internal couple o yung internal moment capacity ng section. So dapat, yung result nito, sa yung transform area, considering moment of inertia, dapat parehas lang. Okay? So let's try to solve considering the transform area method. Okay, so in the transform area method, the first step is to locate the neutral axis. So nakita natin siya. The neutral axis natin is X. Okay. Drawing natin para mas maganda. Okay, so ito yung neutral axis. So ito yung beam section natin. Compression. Ito yung transform area. Is given to N times AS, which is equal to 9 times 1,940 millimeters squared. So yung centroid natin is 171.71 millimeter. Then this value, the centroid of these bars, okay, the centroid of the transform area is 425 minus x over 3, 367.76. So 367.76. Okay. So what is ano pa kailangan natin para makuha natin yung moment of inertia? Wala, di ba? Okay na. Okay. So the moment of inertia ay NA. So moment of inertia about neutral axis, so ito yung neutral axis natin. It's just simply B h cubed over T. So the moment of inertia of the rectangular section at the base is BH cubed over 3. So this value is 300 millimeter. So BH cubed over 3 plus. Okay, so ito, wala tayong dimension. Okay? Wala tayong B, wala tayong H, wala tayong B. Although meron siyang effect, but compared to dimension of the beam, napakaliit niya kasi yung lang natin, kung ito yung bakal natin, ang assumption natin, ito yung centroid mo. Ikakalat mo lang siya into equivalent concrete section. Wala siyang prescribed dimension. Okay? So, we just assume that the centroidal moment of inertia of this is negligible or napakaliit compared to the transform moment of inertia to the centroid. So, in this, still, the transform area method is just simply A, D squared. So, where A is the area, and D is the distance from the centroid of the section or the under consideration the centroidal axis. So the moment of inertia about neutral axis just simply 300 times h. So ang h natin is 171.71 cube over 3 plus AD squared. So yung A natin dito is equal to N times AS. So 9 times 1940 times D, distance from the centroid of the steel to the centroidal axis of the section, 367.76. So this will give the centroidal moment of inertia of 1/3 times 300 times 171.71 cube plus 9 times 1940 times d squared, so 367.76 squared. So this will give 2.868 times 10 to the 9 millimeter to the port. Okay. So considering steel, the basic stress formula, stress is equal to mc over I. Okay? So considering steel, considering concrete, so mc just simply stress times moment of inertia divided by c. So stress is 0.45 square root of F prime C. As it, okay. May mali tayo sa gawa pala kanina. So, yung FC natin, dapat pala sa square root of F prime C. So, bawin na natin to. And so, dapat 0.45 F prime C siya. So, 0.45 times 20.7. So, 9.315 megapascal. So 0.45 times 20.7. Okay. Stress times I. So the moment of inertia is 2.868 times 10 to the 9 millimeter to the port divided by C. So yung C natin is 171.71 millimeter. So MC is now equal to 0.45 times 20.7 times 2.868 e to the 9 divided by 171.71 divide 1,000 squared. 45 times 20.7 times 2.86 to the 9 divide 171.71. So the moment capacity is 155.584 kilonewton meter. Then considering steel, the moment capacity is just simply MS equal to Fs times I divided by Y. So yung Y natin dito is 367.76 millimeter. So, but in determining for I, ang ginamit natin is convert natin yung steel into equivalent area of concrete. So in this case, ang ginagamit natin is yung stress ng steel. So we just simply divided by I with the N or divided by Fs divided by N. So dapat dito, yung I natin, meron siyang denominator na N para homogeneous siya. Still din yung moment of inertia natin. So this will give 140 times 2.868 times 10 to the 9 divided by L9 divided by 367.76 millimeter. So yung MS natin is 140 times 2.868 to the 9 divided by N by 367.76. So the moment capacity is 121.31 kilonewton meter. Okay? So again, mas maliit pa rin yung moment capacity ng steel compared sa moment capacity ng concrete natin. So meron pa tawag natin na magpipil muna siya dun sa steel section compared dun sa concrete. Okay? So, for rectangular section, okay, so instead of doing this napakaraming solution, we can derive the formula for rectangular section. But this is only applicable for rectangular section. For other shapes, kailangan bumalik ulit dito sa transform area method. Okay. So for rectangular section, para sa bilis yung analysis natin o pag-solve natin ng capacity ng section. Okay. So let's say for example, we have rectangular section in with B and H and corresponding AS. So in this problem, in this derivation, we are going to derive the capacity of the section, meaning investigation siya. So for investigation, the dimensions are given, the area of steel are given, okay? So what we need to do is to determine the capacity of the section. So similar to transform area method, so ang gagawin natin is ganun din, kukunin natin yung centroidal moment of inertia o yung centroid nung section. So, the stress diagram is equal to FC. So, ito, linear. So, FC. So, this centroid, so gagawin natin, fraction of depth. So, let's say the centroid is equal to KD. So, meaning, the K value is less than 1. Okay, to solve for the centroid. So let's say this is KD, the distance from the centroid to the outermost fiber in compression. Then the distance from the centroid of reinforcing steel bars to the centroid, okay, of the section is D. Okay. this distance d minus this distance. So just simply d minus kd. Okay. Then the internal couple, okay, the centroid of the compression, so for the triangular section, the centroid is 1/3 of the height of the triangle. So this is equivalent to kd over 3. Then the compression is simply the area of this triangle, 1/2 FC times kd, 1/2 FC times kd times B. So yun yung volume. Ito yung compression. Then distance from the tension steel bars to the centroid of compression concrete is just simply J times D. So ibig sabihin, lahat ng variable natin, lahat ng dimension natin is a fraction of D. Then the tensile reinforcement or the tensile stress T is equal to AS times FS. Okay, so similar to what we have did in the example, kukunin natin yung centroid nung section. So again, the moment of area above, okay, the moment of area above is equal to the moment of area below. Okay, so the moment of area above is B times KD over 2. Ito yung centroid niyan. Okay. B times KD over 2. So it's equal to the moment of area below. So the moment of area below is N ES. Okay. Yun yung transport area ng concrete, steel equivalent concrete, times the lever arm. So the lever arm is D minus KD. So times D minus KD. Okay. So we can say the reinforcing ratio is equal to AS over BD. So ito yung tinatawag natin na steel ratio. Okay. So the steel ratio is the area, total area of reinforcing bars, tension reinforcing bars, divided by the dimension B and D. So take note that the dimension B and D, yung D natin dito is the centroid or the effective depth of the section. So in this formula, we can say that AS is simply rho BD. So if you substitute AS to rho BD, KV squared over 2 is equal to N. AS is rho BD times D minus K. Okay, so we can cancel out B. Okay, we can cancel out D squared. So D squared, so dito magiging 1 minus K. Or just simply K. K squared. K squared is equal to, so 2 N rho times 1 minus K, or just simply K squared is equal to 2N rho minus 2N rho K. So this is quadratic equation. So we can solve for the value of K. So just simply by completing the square, So k squared plus 2n rho k minus 2n rho is equal to 0. So para ma-complete mo yung square mo, ano kailangan dagdag natin? Okay. So, kailangan natin ng k saka n saka rho. So, just k squared plus 2n rho k is equal to 2n rho. So, anong kailangan natin dagdag dito para complete yung square? Anybody? Diba yung x plus 1? Oh, x plus y. So, x plus y times x plus y is just simply x squared plus 2xy plus y squared. So ano yung x dito? Yung x dito is just simply equal to k. So yung 2xy, so 2k, so yung k dito is x. So ibig sabihin yung y natin is nt. So kailangan natin magdagdag ng n rho squared. So since nagdagdag tayo ng n rho squared dito, magdagdag tayo dito ng n rho squared. Okay? So just simply k, diba? K plus n rho squared is equal to 2n rho plus n rho squared. Or k plus n rho is equal to square root of 2n rho plus n rho squared. Or just simply k is equal to square root of 2n rho plus n rho squared minus n rho. So ito ngayon yung value natin ng k. So after solving for k, we can now solve for JD. So in this formula or in this figure, JD is just simply equal to D minus KD over 3. Okay, so we can cancel out D. Or just simply J is equal to 1 minus K over 3. Okay, so in summary, we have K is equal to 2n rho plus n rho squared square root 2n rho plus n rho squared square root minus n rho. Then J is equal to 1 minus K over 3. So after solving for K and D, we can now solve for the internal couple. So hindi mo na kailangan bumalik doon sa kunin mo yung inertia. So pwede ka pa magkamali sa moment of inertia. So just simply solve for the internal moment capacity using this value of K. So, wala ka ng ano, di ba? Ano pa kailangan mo para makuha mo yung moment capacity? So, yung compression is 1/2 FC BKD. So, yung B is the dimension, B and D is the dimension of the beam. And K, ito yung nasolve natin na values. Then, considering the capacity of steel, the sectional capacity is T times JD. So yung common lever arm nila is JD. So either you take moment about the centroid of the concrete or centroid of steel. So JD is already determined. Okay? So from that, okay, the moment capacity, considering steel, is just simply M is equal to T times JT. So moment capacity of steel. Then the moment capacity of concrete is simply 1/2. Okay? 1/2 ng FC. So yung area ng triangle, FC times K. Diba yung sa triangle natin? Ito yung FC. Ito yung KD. Ito yung B. Times D times B. Or just simply 1/2 FC B A D. Okay. So after solving for FC and FS, makuha mo na kung safe yung section mo o hindi. So ito na yung summary ng derived formula natin for K. We have the first equation, K is equal to 2n rho, square root of 2n rho plus n rho squared minus rho n. So paparas lang yun, either gamitin mo n rho or rho n kasi multiplication naman yun, paparas lang yun. Then, yung J natin is just simply 1 minus K over 3. Then, yung Fs natin or yung stress natin. So, normally kasi, ang kino-compare natin, either moment capacity of stress nung section. So, kino-compare natin po into allowable Fs of 140 or 170 kung grade 40 o grade 60. Then, yung FC natin, dapat mas maliit siya dun sa 0.45 F prime C. So from that, you can now determine, halimbawa, kailangan mo naman is kunin mo yung moment capacity. So just factor out the M. Okay, so ipon mo lahat doon para makuha mo yung MC. And for MS man, kunin mo yung MS. So ilalagay mo sa kabila. Okay, or ito, doon mo doon para yung MS natin o yung moment of section natin, MS, considering steel, is AS Fs times JD. So dito naman, yung MC natin is just simply 1/2 FC BD squared KJ or JK. JK. So from this, you can solve for the moment capacity of the section. So yun yung yan naman yung capacity niya considering investigation problem. Then of course, sa design problem, okay, sa design problem, same din yung stress diagram niya, but in this case, unknown naman dito is yung B, yung H, saka yung AS. So similar to the derivation of investigation problem. So dito naman, ang kinconsider natin is yung stress diagram. So yung stress diagram natin, okay, so ito yung FC, ito yung KD, ito yung FS over N, okay, then ito naman yung D, o effective depth. So similar triangle, so this triangle is just simply equal to the bigger triangle. So ito project natin ito doon. So ito yung FS over N. So yung ratio niya is FC over KD is equal to FC, so this big triangle, plus FS over N divided by D, or you can cancel out D. So magiging K is equal to FC over FC plus FS over N. Or just simply, pwede rin K is equal to, para matanggal mo yung divided by N sa FS over N, so just multiply both sides by N over N. So NFC over NFC plus FS. So same lang yun. Then, similar manner, so in determining for JD from this figure, okay, so JD is simply equal to D minus KD over 3. So D will cancel out. So J is just simply 1 minus K over 3. So this is also similar to investigation problem. So the only difference lang in the formula is the determination of K. So ito yung pag-solve ng K for investigation problem. And ito naman yung determination for K will be design problem. Kasi sa design problem, lahat variable, yung B, yung D, saka yung AS. Kaya dapat, ang aim mo lang lagi, ano lang yung given variable. Kasi dito, hindi mo pwedeng gamitin to kasi ano mo yung AS. So yung AS natin, AS is equal to rho B, D. So ano yung rho mo? So, wala kasing AS. Okay? So in summary, again, so sa design, ang unknown mo is B and D. So if we take moment about the compression, the moment is equal to compression times JD. Yung moment natin, yung stress diagram natin. So ito yung JD. So if we take a moment about the central steel reinforcing bars, M is equal to the compression times JD. Or just simply the compression is the volume, okay? Volume of the triangular portion. So 1/2, this is FC, this is KD. So 1/2 Okay, 1/2 FC times KD times P para buo yung volume times lever arm JD. Or just simply, okay, since sa design, ang unknown natin is B and D. So factoring out B and D. So BD squared is just simply 2M divided by FC times KJ. Okay? So ito yung formula in determining for the dimension of your beam. Dimension. Then for AS, so considering, okay, so take a moment about central compression. So moment T M is equal to T times JD, but T is equal to AS times FS. So M is AS, FS times JD. Just simply factoring out AS, setting unknown natin. So AS is just simply M over FS times JD. So sa design problem, moment na i-consider mo, either steel or concrete, ito yung design moment natin from external forces. So yan yung combination ng dead load or dead load plus live load or dead load plus any other live load. Okay? So these are the summary of difference between investigation and design. So in investigation, the physical dimensions, the beam, and number of bars, sizes are given. Okay. On design, the member size are to be determined and AS. So in summary, these are the formula used in investigation, and this one is for design. So take note that in determining for J, parehas lang siya. Okay? Ang pagkakaiba niya lang is yung K. Then this one, we are comparing distress or moment. So either stress, FC, dapat less than 0.45 F'(C), or yung FS natin less than 140 for grade 40 and 170 for grade 60. Or in case of moment, so yung moment natin, so just factor out the M para makuha mo yung moment capacity ng section considering steel and concrete. Then for this time, ang aim natin is to determine the dimension. Then after determining for dimension, solve for AS. But the problem is, this BD are both variables. So hindi natin siyang parehas siyang unknown. So normally in the design, ang ginagawa lang is mag-set ka ng value ng B. Okay? Let's say, for example, 300 or sometimes ratio B is 1.5D to 2.5 either D is 1.5B or 2.5B. So yung ratio nito, okay, yung assumption nito is depend on the designer. So normally, nag-i-start tayo kung ano yung minimum requirement ng code. So normally, yung code, ang minimum dimension ng B niya for special moment resisting frame. Okay? Ito yung mga seismic requirements. So the minimum dimension is 250 mm. Kaya pag wagwan mga residential housing or mga small low-rise building, so kadalasan start tayo doon sa minimum requirement. But of course, mas malaki yung, sa design kasi, habang mas malaki yung depth mo, mas efficient yung section natin, mas malaki yung moment capacity niya. Okay? Kasi habang tumataas siya, andito yung lumalaki yung lever arm o yung beam natin lumalaki. So pag lumalaki yung lever arm natin, di ba yung formula natin, lever arm, JD, is directly proportional to the moments. So moment sa steel is T times JD, moment sa concrete C times JD. So meaning, habang lumalaki yung beam mo, tumaas yung section mo, lumalaki yung capacity ng section natin. Kaya lang, of course, meron tayong mga requirement, like for example, may architecture requirement na nililit lang yung size ng beam natin. So hindi yan pwede masyadong lakihan. So natin i-follow kung ano yung requirement ng client. Okay? So these are the design consideration, okay, for the beams. So first is we need to estimate the beam. Since wala ka pang dimension ng beam, how can you solve for the beam weight? So normally, in my practice, ang ginagawa ko is 10% the dead loads, okay? O 10% ng dead load plus live load, yun ang ina-apply kung additional weight ng beam. Or sometimes, pag may 20%, so depende dun sa nakuha ninyo sa mga design. Kasi ang ginagawa naman natin kasi kadalasan, magkasuka 10%, tapos pag nakuha mo yung beam size, i-check mo kung tumatama ba yung 10% mo. So pag kulang siya, ibalik ka ulit, i-compute mo ulit yung section o moment ng actual moment, then check mo yung capacity. Hanggang sa dating point na in-assume mong weight ng beam is equal dun sa nakuha mong design dimension. Okay? Then for beam proportion, so for most economic section, so yung ratio ng B and D is 1/2 to 2/3. Okay? But this is only applicable for short span, 6 to 7 meter length. But for longer span, mas maganda lalim mo yung beam mo, okay, para malaki yung section capacity niya. But again, depende pa rin doon sa requirement ng architect o ng owner. Kasi minsan may mga owner ay makita ng structure, ay makita ng beam, mga natin, structural members natin. Okay? Then, another consideration is selection of bars. Okay? So, in selection of bars, dapat yung section mo, okay, nakakuha ka ng B and H, tapos nakakuha ka ng AS, so checkin mo kung kakasya yung bakal mo. Baka naman sa sobrang dami ng bakal mo, masyadong congested na hindi nakakasya yung bakal mo sa specified dimension ng beam o yung beam width. Okay? So yung bars natin, size ng bars natin, pinakamaliit is 10 mm. Although may mga available din sa hardware 8 mm, but bihira din gamitin yung 8 mm. So meron 10, meron 12, meron 16, meron 20, meron 25. Dati meron 22 pero ngayon parang hindi na siya available sa market. Bihira makita ng 22 ngayon. 25 plus 28, 32, and 36. So ito mga readily available. But for special construction, like for sa mga bridges, meron tayong bars as big as 51 millimeter diameter. Pero ano yan, by order basis. Okay? Then, another consideration is the cover. So, the purpose of cover is for the corrosion protection. So, kung ito yung beam mo, meron kang bakal dito. So, kailangan mo siya i-protect para huwag siyang kalawangin. Otherwise, pag nalawang yung reinforcing bars mo, mag-deteriorate yung capacity ng section. Kasi pag kinalawang siya, kinain ng kalawang, liliit na yung steel. Okay? Steel area natin. And also, aside from protection from corrosion, this cover will also serve as the fire protection. So pag nagkaroon ng fire, okay, mapoprotect niya yung bakal. Yung bakal natin, when subjected to heat, melt down siya. So babagsak yung structure. Okay? And also, another requirement is the spacing. Okay, so there is a specified spacing ng mga bakal. So hindi basta nakagawa ka ng bakal mo, nakapag-layout ka, merong requirement yan ng NSCP. So the requirement of NSCP, at least minimum 25 millimeter diameter of bar or 4/3 nung size nung aggregate. Kasi pag less than 4/3 nung aggregate, ang tendency is hindi ka kasya. Okay? Hindi ka kasya yung ang grabe mo dito, magkakaroon ka ng ampaw sa ilalim, hindi siya malagyan ng konkreto. Also, meron tayong prescribed by code na minimum steel percentage. So yung Romin natin is maximum between square root of f prime c over 4 fy or 1.4 over fy. So ito yung prescribed ng code na minimum AS natin. Okay? Otherwise, pag masyadong maliit masyado dito yung AS natin, the tendency of this section is magkakaroon ng cracking. Kaya dilisan din natin yung beam natin in such a way that the required area of reinforcement is greater than the cracking moment para wag mag-crack yung section natin. Okay? And also, you can violate this one, okay, provided that your AS is 4/3 of AS. So if AS na to is based on flexure. Okay? So pwede mo i-violate to provided na at least 4/3 AS required by flexure. Halimbawa, ano pa mo sa flexure 100 millimeter squared. Okay? Ang requirement ng code minimum is 200 millimeter squared. So 4/3 of 100 is how much? 4 by 3 times 100 is 133 millimeter squared. So you can violate this one provided na ipoprovide mo is 4/3 ng required AS by flexure. So in this case, 133 millimeter is acceptable na area of reinforcing steel. Okay, so in NSCP, these are the prescribed minimum requirement or minimum concrete cover. So if the member is cast permanently in contact with the ground, so ito yung mga foundation natin, mga footing. So the minimum cover should be 75 millimeter. When exposed to weather or in contact with the ground, okay, for 20 to 50 diameter, we have 50. For 60 millimeter and below, we have 40. So what is the difference between exposed to weather or contact with the ground and permanently contact with the ground? So ganito yun. So meron tayong footing. Baka meron kang footing. Ito yung hukay niya. Ito yung required section footing natin. Ito yung footing bars natin. Pag sinabi natin permanently contact in the ground, ibig sabihin, wala siyang forma. Okay? Sa footing natin, dito pwede lagyan ng forma. Pero dito, hindi pwede malagyan ng forma. So ito yung sinatawag natin na permanently in contact with the ground. Pero yung mga footing tie-beam natin, although in contact siya with the ground, iba yung footing tie-beam natin, yung footing natin. Okay. Meron tayong tie-beam minsan. Tapos ito pa yung ground level natin. So yung tie-beam natin, pag ginawa mo yung section dito, ganito yan. Okay? So nilalagyan natin ng forma dito, minsan lagyan natin ng forma dito. Okay? So ibig sabihin, control pa rin yung concrete cover niya. Kasi nami-maintain natin dito yung meron tayo dito yung tinatawag na spacer block para ma-maintain natin yung height. But dito, in this case, although meron tayong spacer block, but there's a tendency that during pouring, lulubog konti. Kasi kung lupa lang ito, lulubog konti yung bakal mo. Kaya mas malaki yung prescribed or specified cover pag permanently contact with the ground and in contact with the ground. Then for or not exposed to weather. Ito yung mga beam natin na nasa interior, okay? Hindi siya exposed sa rain, hindi siya exposed sa mga other chemicals. So for 40 mm to 50 for subs, okay? Ito yung prescribed niya, 40 and 20 millimeter. For beams, okay? So for beams, columns, pedestal, okay? So any diameter of beam and column, the required minimum cover is 40 millimeter. Okay? Ito yung code requirement. Okay? So pakibago nyo lang yung mga old NSCP. So old NSCP kasi nakalagay 50 millimeter, but it should be 25 millimeters. So the minimum spacing, clear spacing, okay? Clear spacing between bars. So 25 millimeter diameter of bar or 4/3 of size of aggregate. But for columns, okay, so this one is for beams. Then for columns, okay, for columns, the required clear dimension is bigger. Okay, 40 millimeter, 1.5 dB, and 4/3 of aggregate. Then for sometimes we have multi-layer rebar. In mga cases kasi minsan hindi kaya sa one layer lang, so kaya ng 2 layers na reinforcing bars. So the minimum requirement by code in layers, it should be 25 millimeter or bigger. So ito yung minimum requirement ng code. Okay, then in the since sa design, unknown mo yung B and H saka ES. So sabi ko, pwede yung magbigay ng dimension ng B, okay? Pwede yung fix siya, pero yung H nyo, so pag fix natin yung B natin, okay, makukuha natin yung H. But take note, na ang solve natin sa formula is D. Ito. So H is just simply the total height. So how do you get the total height? So let's say for example, meron tayong beam with reinforcing bars like this one. Then meron tayong stirrups. Okay. So ito yung D. So H is just simply D plus, so D is centroid of your reinforcing bars. So plus 1/2 diameter of bar plus diameter of stirrups. Okay, diameter of stirrups plus concrete cover. So once you solve for H, okay, meron tayong prescribed minimum depth of non-distressed beams. So yung mga beams o yung mga structure where using bars lang, concrete plus deformed bars. So for simply supported beam, the minimum height is L over 16, where L is the span length. So ito yung span length. So ano ba yung span length? Yung span length is the distance, the clear distance between columns. So ito itatawag natin na span length. So for simply supported, okay. So for simply supported, span length divided by 16. 1 end continuous, okay. So meron tayong yan. So ito tinatawag natin na beam with 1 end continuous. So ito isang end nila continuous, the other is discontinuous. The minimum H of height is L over 18.5. So for both end continuous, L over 21. So yan, meron tayong another beam. So ito both end continuous. So itong beam na to, okay, both end continuous, L over 21. Then for cantilever, L over 8. So yung cantilever natin, yung mga beam natin na bawa ito. mga bearings. So ito yung cantilever. So cantilever, L over 8. So makikita ninyo, pag cantilever, mas makapal yung required na H compared to other support condition ng beams. Okay. So any questions before we go to the another problem? Okay. Any questions?
Wala naman po, sir.
Okay. Okay. So let's try this simple problem. Simple supported beam with span length 5.5 and total load of 20 kilonewton per meter. Okay. So the concrete efficiency at 28 days is 21 megapascal and 276 megapascal reinforcing bars. So in some other books for grade 40, sa makita nyo 276 or 275. So any will do. So as long na for grade 40 siya, you can use either 276 or 275 megapascal. Okay. So with this problem, of course, we need to approximate the weight of the beam since wala pa tayong dimension ng beam. So let's say we assume that the self-weight is equal to 20% of the total load. So meaning the total load, including the beam weight, is 20 times 1.2, just simply 24 kilonewton per meter. Okay. So this is a design problem. Okay. So in design problem, ang kailangan natin kunin yung value ng K. So for design problem, ang K natin is equal to NFC over NFC plus Fs. So N natin is just simply it's equal to ES over is of C. So ES is 200 times 10 to the 3 megapascal divided by EC of 4700 square root of F prime C. So F prime C natin is 21 megapascal. So ang N natin is just simply 200 into 3 divided by 700 square root of 21. So N is 9.28. So say N is 9. So in determining for N, always use the whole number lang. Okay? So just neglect the decimal. Okay. So what else? Wala na. Meron tayong FC, 0.45 of prime C. Fs is given. So Fs for grade 40 or 276 megapascal is 140 megapascal. Okay. So let's say, for example, this problem, the problem states that use B is equal to, let's say, D over 2. Okay. So we can now solve for K. So K is equal to N, which is 9, times 0.45, 21 megapascal, divided by NFC, so divided by NFC, which is 9 times 0.45 times 21, plus Fs. So Fs is 140 megapascal. So take note that your K should be always less than 1. So 9 times 0.45 times 21. So A is 0.378. Okay. So now we put the value of K. So we can now solve for J. So J is equal to 1 minus K over 3, which is equal to 1 minus 0.378 divided by 3. So K is J is 0.874. Okay. So knowing for the value of K and J, kailangan natin, we can solve for the dimension. So from the formula, okay, for design, BD squared is equal to 2M over FCK KJ. So BD squared is equal to 2M divided by FC. Okay. KJ. So KJ. So for simple supported beam, the moment M is equal to WL squared over 8, which is equal to, so W natin is 24 kilonewton per meter times length of 5.5 squared divided by 8. So 90.75 kilonewton meter. So from the problem, it was stated that B is equal to 1/2 D. Okay? So substituting 1/2 D times D squared is equal to 2 times M, so 90.75. So gagawin natin Newton millimeter. Newton millimeter yung values natin. Okay, so times 10 Newton millimeter divided by FC is 0.45, F prime C 21 Newton per millimeter squared times K. So K natin is 0.378 times J natin o 0.874. So from here, D is equal to, so can you solve for the value of D? Yan yung value ng D. Can you solve? Yan yung D. Okay, anong value ng D? Or 88.08. Okay. So D is 488.08 millimeter. So B will now become 1/2 of D, or just simply 1/2 times 488.08. Just simply, so 488.08 divided by 2. So 244. So 244. Oh, wala. So 244. 244.04 millimeter. So in summary, let's say this one is, so lagi pag design tayo ng beam, kinukonsider natin yung dapat hindi exposed either by 25 millimeter or 1 inch or 2 inches or 100 millimeter. So in this problem, okay, let's say D is 490. So kasi dito, hindi pa naman siya H. So 490 millimeter. But your D natin, so round off natin siya into nearest 25 millimeters. So let's say D is 250 millimeter. So from that, we have now the value of B and D. Next is to solve for AS. So AS natin is M is equal to AS RS times JT. So moment natin is 90 or just simply AS is equal to M. So 90.75 times 10 to the 6 Newton millimeter divided by Fs of 140 times J of 874 times D of 490 millimeter. So AS is 90.75 into the 6 divide 140 times 0.874 times 490. So AS is 1,513.6 millimeter squared. So we have now AS, B, and D. Ano ba yung tanong sa problem? Ang tanong sa problem is design the beam. Okay. So let's say we are going to use 25 millimeter bars. Let's say 25. Yun ang problem pa, parang pag-block, ayaw nyo magsulat palagi. So let's say we use 25 millimeter diameter bars. So for 25 millimeter diameter bars, ang area niya is ang area niya is 490.87 millimeter squared. So the number of bars N is just simply AS over AS of 1 bar, AST. So 1513.60 divided by 490.87. So this is equal to 3.08. So say N is equal to 4, diameter 25 millimeter. Of course, pag nag-design kayo, dapat laging kukunin nyo yung next number. Hindi ka pwede mag-design na, bawa, 3 bars, kukulangin siya. Okay? So next is, after determining for the number of bars, check na natin kung kakasya ba siya dun sa dimension nung natin. So otherwise, we need to revise the B or we need to revise the diameter of the bars. Okay. Okay, so yung D natin, So yung dimension natin ng beam, so we have 4. 1, 2, 3, 4. So ang beam natin is 490 millimeter. Then meron tayo H B na 250 millimeter. So checkin muna natin kung kasya ba yung 4 na 25 millimeter. So sa 25 millimeter, okay, yung dapat na clear distance niya should be 25 millimeter. Diameter of bar or 4/3 nung aggregates. Since hindi specified yung aggregates natin, okay, so let us assume na ang gagamitin nating aggregates is smaller, ikakasya dun sa bakal. So, for 250 millimeter, we have 1, 2, 3. 3 clear, okay? So, sa beam natin, yung meron tayong stirrups. Since the problem, yung beam natin is not exposed to weather. So not exposed to weather siya, ang concrete cover natin is 40 millimeter. So let's say, for example, the diameter of bars or stirrups is 10 millimeter. So normally, 10 millimeter is small stirrup sa ginagamit natin. Okay? So in this case, ito yung beam natin. So yung clear spacing natin, C, is equal to 250. Yung total width ng beam. Minus dalawang concrete cover, 2 times 40. Minus 2 times stirrups, 2 times 10, okay, minus ilang bars, 1, 2, 3, 4. So we have minus 4 times 25 divided by 1, 2, 3 divided by 3. So yung clear distance natin is 250 minus 2 times 40 minus 2 times 10 minus 4 times 25 divided by 3. So clear distance lang natin is 16.67 millimeter. So this is less than 25 millimeter. So it just so happened that the diameter of bars is 25. So ang governing clear distance natin is 25. So ibig sabihin, yung arrangement ng bakal natin is hindi kakasya dun sa required clear spacing ng bakal. So what we need to do is we check if, okay, naka-bundle siya, 2-bar bundle. So ang clear spacing niya dapat is at least 25 millimeter. Pag 2-bar bundle, the clear spacing C is 250 minus twice the concrete cover minus twice the diameter of stirrups minus 4 times diameter of bars divided by, since one spacing na siya, 1 lang siya. So ang clear spacing niya will be 50 millimeter. So this is greater than 25 millimeter. So meaning, para pumasa siya doon sa concrete cover requirement natin or sa clear spacing requirement ng code, kailangan mag 2-bar bundle tayo. Okay? Then next is, what is the total depth or total height of the beam? So the total height of the beam okay. So the total height of the beam, ito naman. So the total height of the beam meron tayong 2-bar bundle with steps. So the effective depth natin D is equal to 490 millimeter. Okay. So the total height H. So H is equal to 490 plus, okay, 1/2 of diameter of bar. So 1/2 times 25 plus diameter of stirrups, which is equal to 10 millimeter. Okay, plus the concrete cover of 40. So the total H is equal to 490 plus 0.5 of 25 plus 10 plus 40. So the total height is 552.5 millimeter. Of course, hindi ka naman mag-specify na decimal place yung height nung beam mo. So either you can use H equal to 575 millimeter or 600 millimeter. So, but the best is to use 600 kasi kadalasan yung mga forma natin is mga modular forms natin, ang sizes niya, mga beams natin na mga forma, ang ano niya, ang increment niya is 100 millimeter. So, depende sa designer, either 575, yung forma mo, ibaba mo ng konti dito, okay, na mahirap gawin. Okay? Or gawin mo 600 siya para diretso yung modular na forma mo. So either 25 mm increment mo dun sa height ng beam, pwedeng 50 mm or 100 mm. So depende kung anong gagamitin yung pang-forma. So pag manong forma, yung plywood lang o formworks na pinaulit, pwede kang 25 mm. Pero pag mga prefab na form, either 50 or 100 mm yung gamitin mo. So in final design, yung beam natin, ito na siya. 2-bar bundle with stirrups. So dimension niya, B niya is 250 mm. And total height niya ng beam natin is 600 or 575 millimeter. Okay? So although in design, theoretically, i-design natin siya as steel reinforced, but the code requirement and in practice, we are providing at least 2 bars on the top. So the purpose of this is to hold the stirrups, okay? Then second is, siyempre sa beam natin, pag sa continuous beam natin, di ba yung bending moment natin, pag ganyan. Okay? Sa midspan, tension siya. Pero pagdating support, tension niya is nasa top. Okay? So at least you provide additional 2 bars to support for the stirrups. Okay? Then, i-check mo ngayon to kung more than siya dun sa minimum requirement ng code. So, ano ba yung minimum requirement ng code? So, square root of F prime C over Fy or 1.4 over Fy. So, square root of F prime C square root of 31 divided by 4 Fy. 4 Fy is 276 times CD. Diba yung rho natin should be greater than or equal to F prime C over 4 Fy or 1.4 over Fy. So B natin is 250. Then D natin is, so now meron na tayong bagong D. So yung D natin ngayon dito, yung D sa design kanina is 490. Kaya lang, in-adjust natin para maging sakto siya dun sa full number. So, ang D natin ngayon, the actual, is now equal to 600 minus concrete cover of 40 minus diameter of syrups of 10 minus 1/2 diameter ng bar na 25. So the actual D provided is 600 minus 40 minus 10 minus 0.5 or 25. So the actual D is 537.5. So the AS minimum is 250 times 537.5, which is equal to 21 divided by 4 times 275. So 276 times 250 times 537.5. So this is 557.78. So yung 1.4 over FY, 1.4 over 276 times BD, 50 times 537.5 is equal to 1.4 divided 276 times 250 times 537.5. So this will give 681.61 millimeter squared. So this is less than the provided AS of, yung AS natin, 4 na 25. So 4 times pi over 4 times 25 squared. So this will give 4 times pi divided 4 times 25 squared. 1,963 millimeter. So yung final design ng beam natin, ito na yan. So bigger than, okay, nasatisfy natin yung minimum spacing. Nasatisfy natin yung minimum row. Okay. So for that, yan na yung ipagawa mong design o ipapadrafting mong design dimension and AS requirement ng beam. So any question? Meron pa yung questions? Clear ba sa lahat? So design ng single reinforced rectangular beam using working stress design. Okay. So meron questions?
Pwede po makuha po yung PowerPoint po.
Yeah, i-upload ko yung PowerPoint dun sa, sa Google Classroom natin. Okay. So kung wala ng questions, next meeting we'll be discussing double reinforced rectangular beam and regular beam plus additional exercises considering ito naman ang ginawa natin is design natin yung beam, and then i-check naman natin after design ano yung capacity niya, okay, para kumpleto na yung design and investigation problem natin. And then since yung double reinforced saka irregular beam, siguro mga 1 hour lang yun plus 30 minutes problem. So we can continue with the ultimate strength design. So expect nyo on the next meeting, after the next meeting, yun yung first question nyo. Pero ang combination lang will be the working stress design. Okay? So may questions pa? Any clarifications? Okay, so kung wala ng questions, we continue next meeting. See you next meeting. Good night, everybody.
Good po, sir. Thank you po.
Thank you po, sir.
Good night po. Thank you po.
Thank you po, sir.
Thank you po, sir.
Thank you po, sir.
Salamat po.